Okay, so new topic, section 6, primary decomposition. So what is it all about? So when you're dealing with integers, you can decompose every integer as a product of powers of primes. When you have a polynomial over a field with one variable, you can decompose it into products of linear factors. And the question is, to what extent can it be done over a general ring? And that's what we're going to try to do. We're going to try to decompose ideals into, roughly speaking, products of primes, but it's not exactly that. Okay, so there are complications, but that's the goal. Okay, so we start straight away with proposition 6.1. So R is a ring, as always. Let R be a ring. There are two statements in this proposition. First of all, suppose that we have a bunch of primes, P1 up to Pn, or Pk, just to stay true to the notes. They sit inside the spec of R, and we have an ideal. I is an ideal. Now, suppose that, so if the ideal sits inside the union of the primes, then it actually lies in one of them. There exists I0 such that I sits inside a single prime. Okay, if you live in the union of primes, then you live in one of the primes. And item 2, it's similar. So now we are going to have a bunch of ideals, ik ideals in R, and P is a single prime. If now if the intersection of the ideals lives inside the prime, then one of them lives inside the prime for some I0. And moreover, if the prime is actually equal to a product, sorry, the intersection of the ideals, then it's equal to one of them. Okay, so these are the statements. They will be useful throughout the lecture today. So let's prove it. I mean, let's prove them. Proof. Okay, so the first item is a proof by induction. This is an induction on K. What's the first case? Well, if K is 1, then we have an ideal sitting inside the prime, and the conclusion is that the ideal sits in the prime. So there's nothing to check. Okay, immediate, so clear for K equals 1 is just a tautology. So now suppose that it holds for K. Let's say that it holds for K minus 1. So for general K, what do we do? So we have two cases. So it could be, first of all, it could be that I actually sits inside the union of the primes, but now the i's are all except some particular j, for some j. If they sit in the union, but we don't have to use one of the primes, that means that I sits in the union of at most k minus 1 many primes, so it's the inductive step. Okay? Then we are done by inductive step. And we are done by the inductive step. Okay, so now we are going to look at the case. So now suppose that for every j, it is not true that I sits inside the union of the primes take away the jth one. So it cannot be, we cannot get rid of one of the primes. So this means, so the fact that this is not a subset of that has to be witnessed by an element. So for every j, we are going to have an element which I call xj. And this guy is going to lie in I, but not in the union of I not equal to j prime I. Okay? Are we happy about this? So we do, and yeah, so in other words, but I is in the union of all the pi. So in other words, xj lies in pj, because it lies in I, and I is covered by all of the primes, and xj is not in pi for every I different than j. That's just a reformulation of the same thing. Okay, so we have these elements, they lie in I. So we are going to take an element y, which is going to be a sum of j going from 1 to k of things of the following form. I'm going to take x1 times x2 times blah 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 times xj minus 1 times xj plus 1 times xk. Okay, with the obvious notation when j is equal to 1 or k. If you are doing topology, topology is often denoted by putting a hat. Okay, so topological notation would be I will put the xj in here, and I will put a hat on top, which means that it's missing. Okay, so I'm taking the product of all the elements xi except for the jth one, and I'm taking the sum of all of those when j varies. Okay, why would I do this? Well, so each of the I x's are in I. So we certainly have this guy sitting in I. But we know more. So the element x1 times x2 times blah 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 xj minus 1 xj plus 1 xk, where does it lie? Well, it's going to lie inside of p, let me just be clear, in pi for every I not equal to j, right? Why is that? Let's see. That should be clear. Let's see. So each of the x's, right. So if I look at pi, I is not j. There is the corresponding xi. Xi lies in pi. Pi is an ideal, so it follows. Okay, so that's what we have. So that's good. But now the element y lies in I, but I lies in the union of the primes. So there exists some particular I such that y lies in pi. Okay, so now we are happy, because this means that if I take x1, x2, blah blah blah, xi minus 1, xi plus 1, is this I, blah 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 xk, this is equal to y minus a sum j not equal to I, x1 blah 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 xj minus 1 xj plus 1 blah 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 xk. Oops. This is in pi. These guys are in pi. So this is in pi. Okay? I have this guy is in some pi. Each of those except for one is in pi. So the one that I threw out has to be in pi as well. But now pi is prime. So at least one of these guys has to be inside. At least, not must. One of x1, x2, xi minus 1, xi plus 1, xk lies in pi, but that's a contradiction. None of them does, right? Because we know that they don't. Okay, so that's how we finish proving item 1. Okay, so let's prove item 2. So there are two statements. We are going to prove the first statement first. So we have a collection of ideals. We take the intersection lying inside of a prime. Okay, so so suppose that the intersection of suppose that it's not true that one of them lies in the prime. Okay, so this is not true for every I. So that this gives us elements. So there exist elements xi lying in ii, but not in the prime for every I. Okay, but now let's take a product. So the product x1 blah 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 xk, where does it lie? Where so each of them lies in ii. So the product certainly lies in the intersection. Yeah, it's easy to see. They definitely lie in every single one of them, and that is sitting inside the prime, and that's the contradiction again, because now P is prime, right? P is prime. So there exists an I such that one of these guys lies in P, but each of them lies outside of P. Contradiction. Yeah, so that's an easier argument, just using primality of P. Okay, so so that was the first part. If you have an intersection of ideals lying in a prime, then one of the ideals has to be in the prime. Now we are dealing with this case. So finally, if the prime is the intersection, we already know that then there is some ii lying inside of P for some I. But of course also P lies inside the intersection, let's call it 0, of these guys, which lies inside ii0, so that's the end. Okay, it's double inclusion. I0 is in P and P is inside ii0. Okay, so that's proposition 6.1. So now we can move straight to a definition that follows this, and we're going to define, so confusingly the definition is going to be numbered 6.3 because there is a remark in between that is in the notes. I'm not going to mention it, but just take a look. And this is very important. So we say that an ideal I inside of R is primary if it is proper and all the zero divisors of R divided by I are nilpotent. Okay, so we are going to decipher this definition in a second, but first of all, let me tell you that primary ideals play the role of prime powers. So when we're going to decompose ideals, if there were numbers, we would decompose them as products of primes, so products of prime powers, and now we're going to do it using primary ideals. Okay, so this is what you should keep in mind as being the analog of a prime power, though it is not exactly the same as the power of a prime ideal. Okay, so be careful about that. But the idea is the same. Okay, so let's decipher it. What does it really mean? So in other words, I is primary if and only if the following conditions hold. Whenever, if and only if, whenever x times y is in I, and x itself and y itself are not in I, then let's think about it. When I take this quotient r over I, x was not in I and y is not in I, so the images of these guys in this quotient are not 0, but they multiply to something in I, so they multiply to 0, so they are 0 divisors. The definition stipulates that 0 divisors should be nilpotent, so these two guys should be nilpotent in here. That's the same as saying that some powers, there exist powers n and k, at least one, such that x to the n and y to the k are both in I. Okay? Does it make sense? That's precisely what the definition says when you unravel it, when you pull it back from R over I to what happens in R. Okay? And in other words, this last bit, okay, there's too much in other words, that is x and y are in the radical of I, because that's the same condition as this. Okay. Right, so we have the definition of primary, and now let's prove a little lemma. 6.4. If I is a primary ideal of R, then the radical of I is prime. Okay, again, what you should think, power of a prime, the radical of a power of a prime ideal is the prime ideal, so it all makes sense. Okay, but again, primary is not the same as being a power of a prime. Okay, proof. Okay, so we are taking x and y in R with x times y lying in the radical of I. Okay, so we are proving primality, so we are going to show that at least one of the elements x or y lies inside of the radical itself. Okay, so the product is in the radical, so that means that there exists some n such that if I raise x and y to the power, which is the same as doing this, this lies in I. Okay, and now we're going to use the definition. So from definition of primarity, hence we have xn in I or yn in I, or finally, if both are not in I, then we know that both lie in the radical. And this is the condition, xn k is in I and yn l is in I for some k and l. Okay, that's the last condition. If one of them is inside of I, x of n or y of n, then we are happy. If neither of them is, then both the elements have to lie in the radical. So that's what it is. Okay, but in this case, when you think about it, it doesn't matter what happens, x or y lies in the radical. If xn is in I, then x is in the radical. If yn is in I, then y is in the radical. If this happens, then both actually of them are in the radical. Yeah, so that's it. So that's primarity of the radical of a primary ideal. Okay, very good. So this lemma is important because it allows us to introduce more notation. Actually, maybe I can fit it in here. So now we can say, so if P is a prime and I is primary, we say that I is P primary if the radical of I is P. Okay, so this is well defined. So every primary ideal is P primary for some P, where P is exactly the radical of I. Okay, again, it gives you the prime that divides your prime power, right? That's the idea. Okay. Okay, but vice versa, this is important to note. If you have an ideal whose radical is prime, it does not mean that it's primary. We are not going to go through a counterexample, but there is one in Atiyah MacDonald. Okay, so take a look if you're interested. And there is a precise, well, it's Atiyah MacDonald chapter 4 is in the notes. Okay, next result, lemma 6.5. Oh, this is kind of cool. So let J be an ideal in R such that the radical of J is maximal. So in particular prime, that is more than prime, then J is primary. Okay, so it's not true that having prime radical ideal is sufficient and necessary to be primary, but it's not so far if your radical ideal, if the radical of the ideal is maximal, then you actually are primary. Okay, well, let's prove it. Okay, so we are going to look at the radical of R divided by J. And now I claim that this is clearly maximal. Why is that? So if you remember, the radical of J, the way it's defined is that you take R, you divide by J, and you look at the nil radical, and you pull it back. Yeah, that's the definition. This notation is precisely the same thing. So if you remember, this is an abuse of notation. When I say radical of a ring, what I really mean is the radical of the zero ideal inside of the ring, which is the nil radical of this ring. Okay, so this is related to that by pulling back from here. This is an ideal in this ring, and Rj is an ideal in R, but it's obtained from this guy by pulling back. So because this guy is maximal, that means that this must be maximal as well. Okay, so this is maximal. This is the nil radical in Rj, since Rj was in R. Okay, just a pullback. Okay. Okay, but that means that the ring R over J is local. Why is that? Because every prime ideal contains the nil radical. If the nil radical is already maximal, then I cannot go beyond it. Every single prime ideal is going to be the nil radical. Okay, so that means that R over J is local. Hence, and this is something we already proved before, every element of this local ring is either a unit or a zero divisor. Sorry, not zero divisor, nilpotent. Sorry. If you are in the nil radical, then you are nilpotent, and if you are not, then you are a unit because of locality. Yeah? Think about it. If I take an element outside of the nil radical, and I take the nil radical and this element and generate an ideal together, it's bigger than the maximal ideal, so it's everything, contains identity, and then there was an argument, we went through it, which shows that the element is a unit. Okay, so that means, every zero divisor is nilpotent. Is nilpotent. And that's the definition of primality of J. You take R mod J and you check if every zero divisor is nilpotent. We just did it. Yeah, so locality of the ring is what does it for us. Okay, good. So that's good. Okay, lemma 6.6. So by the way, from the previous lemma, we see that if you take a power of a maximal ideal, then it is a primary ideal. Why is that? If you take a power of an ideal, then the radical of a prime ideal, the radical is obviously the prime ideal you started with. Okay? So we just proved that if the radical of something is maximal, then you are primary. So if you're looking for primary ideals, taking powers of maximal ideals is an easy way of getting them. Yeah. Okay, 6.6. Okay, this is quite technical, but it's kind of cool as well. So we take a prime and a p primary ideal in a ring R, and we take an element x inside R. So here are three statements. One, if x is an element of this primary ideal I, then this ideal, which we defined in lecture 1, so you surely don't remember, is equal to R. So let me remind you what that is. The notation is meant to be suggestive. This is I divided by x, which means that if I multiply by x, I'm meant to get an I on the left-hand side and Rx on the right-hand side. So the definition of this is everything that divided by x will become an element of I. Okay? Does it make sense? So when you think about it, it is exactly what this notation is suggesting. Yeah? Everything that when hit with x will become an element of I. So if x is in I and I is, well, then I divided by x is everything. We're going to prove it in a second. 2, if x is not in I, then if I take the radical of this ideal, then this is the prime ideal P. And finally, if x is not in the prime, then if I look at this ideal again, it is just I. Okay, so let's do the proof and we will see how it goes. Okay, so 1 and 3 should follow immediately from definition, so let's think about it. If I take an element from I and I hit it with literally anything from R, it stays in I because I is an ideal. So everything has the property that if you multiply it by x, it is in I. That's just this first line. Okay, so 1 is clear. What about 3? 3 should also be clear. If I take x, which is not in the prime, so certainly if I hit x with anything from I, it becomes an element of I because I is an ideal. So that is certainly inside. But can there be anything else? Well, if I take anything else and I multiply by x and then it lies in I, then what should be clear? We should use primarity of I. Let's do it again. Okay, so 1, this is clear. Let's do the third one together. Okay, 3. So if we have some y inside here, that means that y times x is in I. Okay. Now I is primary, so x is not. Let's see. Right. So in the definition of primality, we will have that y is in I, or x is in I, or both are in the radical. But x is not in the radical. Okay? X is not in the radical. So from definition of primality, we need to have that y is in I or x is in I. Okay? But this sits inside the radical. So x cannot be here. Okay? So this proves that all the elements in here are actually in I. Okay? That's how you prove 3. Okay, and finally, the interesting part, which is 2. Okay, so now we take some y lying in the radical of I divided by x. So this means that there exists an n such that, well, y of n lies in this So y of n times x is in I. Okay, that's the definition. Okay, but that means that okay, right. So since we haven't used the assumption yet, since x is not in I, the definition of primality tells us that y of n is in I, or y to the n and x are in the radical. So that means that in either event, y is in the radical. Okay, definition of primality. This is in I, or this is in I. If they're both not, then each of them is in the radical, right? So since x is not in I, either we have that yn is in I, in which case y is in the radical, or y to the n is in the radical, so y is in the radical. Yeah, I'm doing 2 steps at a time. Okay, so since x is not in I, y is in the radical, but that's p. Okay, so this is one direction. We started with y on the left-hand side, and we concluded y is in the right-hand side. And now we have the other direction. Okay, we also have, what do we have? We have I sitting inside of the radical is sitting inside of P. Okay, why is that? Well, that should be clear, so let's think about it. If I hit x with anything in y, it stays in y, so this guy contains y, so certainly y is in here, so y is in the radical. Yeah, so that's clear. Now what about this? Let's see, why does it sit in P? Should be clear, but it isn't. Sorry? No, now I really so we're proving the other direction. I started with the left-hand side included in the right-hand side we proved. So now we are going to prove right-hand side in the left-hand side, but I need this statement because I want to apply radicals to it. So now I'm just worried about this. Why is it true? If we take we prove, oh yeah, it is, right, yes, thanks, right, it is, okay, right, exactly. So this we just proved, okay, yes, good point. So this is trivial, this is what we just proved. Okay, but now I'm going to apply radicals to both sides. So apply the operator, if you want. What do we get? So on this side we get the radical of I. Here we get the radical of the radical. And here we get the radical of a prime, which is the prime again. But what else do we know? We know that I is P primary, so this is P. Okay, so now it finishes the equality because now we've proven that this guy is equal to P. Okay, yeah. I've used the fact that the radical of a radical is the radical. We proved that. Okay, very good. So now a bunch of definitions. We say that an ideal I is decomposable. That's very important. So I should, okay, before I say it, let me say some words. So if we take an integer or a polynomial over a field with one variable, we know that we can always write it as a product of primes or product of linear factors. In general rings, it is not true that every ideal admits such a decomposition. Okay, so we are going to say that an ideal is decomposable if it does admit such a decomposition. I will tell you in a second what this means. But not everything is like it. Fortunately, later on we will be looking at Noetherian rings where it is always the case. Yeah? So for nice rings, the rings that we really want to work with, it's going to work. Okay, so it's decomposable if what? If there exists, okay, let's write it in words, if there is a collection a finite collection J1 up to Jk of primary ideals, which are our proxy for prime powers, primary ideals, such that I is the intersection of the J's. Okay? Think about integers. If you had a number, the way you go to ideals is you generate the principal ideal. The principal ideal being an intersection of other principal ideals, which means exactly the same as the number you started with being divisible by the numbers defining those guys. So that's the exact, is the exact analog, right? So this tells you this ideal is, in a way, a product of prime powers. Yeah. Okay, now, do we say it's decomposable? Okay, such a collection is a primary decomposition. Okay, of I. And finally, a primary decomposition is minimal, which is what we really want, if the two properties, all the radicals R of Ji are distinct. Okay, so we don't want to use the same prime twice. And B, for all I, we have, if we take Ji, it's not true that it contains the products of the J. If we take J, yes, wait, sorry. Sorry, this should be a J, and this is J not equal to I. Okay, what happens? Point A tells us that in our primary decomposition, we might have used powers of the same prime more than once. We don't want that. The second thing tells us that this is just a redundant element. Okay, we don't need it because already, if this contained this intersection, then we don't have to use this guy in our intersection. Yeah, so it was just an extra element in the decomposition that we just don't need. Okay, and now here's a kind of a useful fact. Any primary decomposition can be reduced to a minimal one okay, how? In the following way. The first thing we do is we use lemma 6.7, which we just proved. What does lemma 6.7 say? Where is lemma 6.7? Did I forget to give you one lemma? Sorry. Let's see. Lemma 6.6. Haha, that's funny. Yes, I did. Okay. So let me. Okay, so we are going to do another lemma. Sorry for that. So lemma 6.7, which I forgot to give you, I will give you in a second, will allow you to show that you can always get rid of repeated radicals here. Okay. Okay, so let's leave it like at that for now. And then the second one, which is easy, just remove ideals violating B. Okay, so this is This is easy to do. If you see a ji which contains the intersection of all the other j's, you just throw it out. Yeah, there's no problem with that. Okay, lemma 6.7. Now there's suspense built. What does it say? So let's do it. So we see what the goal of lemma 6.7 is. So let's try to guess the statement. So lemma 6.7. Let P be a prime and J1 up to Jk all be P primary. Then the intersection is also P primary. Okay, now before we prove it, let's see how it allows us to do this. So if you take your collection of the ji's, and it so happens that J1 and J2 are P primary for the same P, you just intersect them, and that's a good enough P primary ideal, and you just use that. So instead of using them, like two of them in the collection, you take the intersection and just put that into the collection. Yeah. So use lemma virtu. Okay, well, it's clear what you do. Yeah, you take two things with the same P primary in the same way, and then you just replace them both by a intersection. Okay, so this is the one thing we need to prove, and we will be doing fine. So let's just prove it. Okay. So we compute if we take the radical of j. Oh, wait. Sorry, this guy should have a name, so I should call it j. If I compute the radical of j, this is the same as, this is a property of radicals that we did prove. I can take the intersection of the radicals. Okay, this is 1 to k. I should say that. Okay, so the radical of the intersection is intersection of radicals, but all of these guys are the same. So I'm taking an intersection of the same prime ideal k times, so it's just this prime ideal. Yeah. So the fact that the radical of j is also p is easy. It does not prove that j is primary, but it proves that if it is primary, it is p primary. That's what it proves. Yeah. So now we have to prove that j is primary. So suppose that x times y, so we take x and y in the ring as always, and the product is in J. Okay? We can also assume that neither of the elements are in J. So the definition of primality, of being primary tells you that if I take a product inside, the first thing is inside, the second is inside, or both are in the radical. So I can assume that the first is not inside, the second is not inside. And now I just need to worry about showing that each of them lies in the radical. Okay? Now, they are not in J, which is an intersection. So that means that there exists I and j such that x is not in ji and y is not in jj. Yeah, because they are not in the intersection. Okay, but the product x times y is, right? So using the fact that ji and jj are primary ideals, we conclude that there must exist numbers, and I call them L and T here, such that, let's look at this guy. So x times y is in ji, because it's in j. X is not in ji. So could be that y is in ji, and if not, both x and j are in the radical. So j to the L is in ji. It's the same argument as we've done 7 times today, right? So, and the other thing we do is just for jj, y is not in jj, so x to the t has to be in jj. Okay, but now x lies in the radical of jj, because its power is in jj. Jj is p primary, so that's p. That happens to also be the radical of j, because we proved it already. So r is in the radical of j, which is good news. But that, of course, is also the same as p again, which is the same as the radical of ji, and that is where y lies. So both y and x lie inside the radical of j, so j is p primary. Okay, this shows that it's primary, and this fact here shows that it's p primary. Okay, good. And now we can use this to finish this discussion here. And the discussion tells us that if we take an ideal which admits any primary decomposition, then it's going to admit such a minimal primary decomposition where I essentially see every prime at most once, and there are no redundant factors. Okay? Okay, so let me just write down, since we actually have time for once, that in general, so be careful with this, in general, not all ideals are decomposable. Okay? But they are if the ring R is Noetherian. Of course, we haven't Noetherian, we didn't discuss what that means, but we will in the sequel. So this is it's a teaser for now. Okay, so let's keep going. So we have a theorem in front of us, or ahead of us, and there's still time. Okay, so here's the theorem, 6.8. Okay, so when we have a number, we can write it as a product of primes, and the primes are unique, right? This is what Euclid proved. So the question in general ring theory becomes, okay, if you have an ideal which is decomposable, perhaps it has more than one decomposition, and it often does. To what extent can we say that, okay, you know, the primes that appear are always the same? Yeah, that's what we want to do. And this is what this theorem is about. So let I be decomposable. Let ji up to jk be primary ideals, with I being the intersection primary ideals forming, a minimal decomposition of I. And let pi be the radical of ji. Then the following two sets coincide. What are the sets? The set of all the primes, okay, I from 1 up to k, and the set of prime ideals among those of the form radical of I divided by x, where x is in R. Okay, so we are not going to have time to prove it, but let's, well, today, let's look at what the statement says. So the first set we are looking at is the set of all the primes that appeared in this particular primary decomposition that we started with. Okay? We can have many different primary decompositions, and this set, in principle, could differ depending on the decomposition. The second set has nothing, the decomposition does not come into the definition of this set. This is the set of ideals of the form I divided by x. This just depends on I, right? Because we look at all x's. We take radicals. So this is a bunch of ideals depending only on I, and then we look at the primes among those. That's independent of the decomposition. Yeah? So once we prove this theorem, which we will do at the beginning of next lecture, we will see, or we will have seen, that the primes appearing are independent of the decomposition that we've used. Okay, so I think it's time to stop. So thank you.